Hey everyone, and welcome to this explainer. I'm your host, and today we are jumping straight into a high-energy exam prep boot camp. We're going to get you totally ready to completely ace your Grade 8 Advanced Science Term 3 test. Let's get focused, keep things beautifully simple, and conquer this material together.
So, here's our game plan for today. We'll be looking at the exam game plan, mastering motion and equations, reading speed-time graphs, all about waves, and finally light and sound energy.
All right, Part 1, the exam game plan. Moving right along to Section 2, mastering motion and equations.
Okay, so the absolute most crucial concept we need to start with is momentum. The best way to think about momentum is just how hard it is to stop a moving object. Mathematically, it's simply the product of an object's mass and its velocity. So really, it's all about how much mass is actually moving and exactly how fast it's going.
And we've got a brilliant visual trick to help you calculate it. Take a look at the momentum triangle on your screen. So P stands for momentum at the top, and then you have mass, m, and velocity, v, at the bottom. If you ever need to find the formula for velocity, you just cover up the v with your finger, and the triangle literally shows you what to do. Divide momentum, p, by mass, m. It's a fantastic little tool to keep in your back pocket during the exam.
Let's actually put that triangle to the test right now. Here is a real practice question pulled straight from your study bank. An object has a momentum of 150 meters per second and a mass of 30 kilograms. Is the velocity 5 meters per second or is it 4,500 meters per second? Take a quick second to think about how you'd apply that formula. Well, let's walk through the math step by step. Step 1, you identify your values, right? Momentum is 150, mass is 30. Step 2, we want velocity, so our trusty triangle tells us the formula is v equals p divided by m. Step 3, we just solve it. 150 divided by 30 gives us exactly 5 meters per second. See? When you break it down into simple steps like that, finding the correct answer is just incredibly straightforward.
Excellent job on that. Now let's shift gears from momentum to acceleration. In plain English, acceleration is simply the rate of change of velocity over time. It's really just a measurement of how quickly an object speeds up, slows down, or changes direction.
Now, what's really interesting here is the formula itself. To find acceleration, we just need to find the change in speed, which is our final velocity minus our initial starting velocity, and then divide that whole number by the time it took. You're basically just calculating exactly how much the speed changed every single second.
Let's look at another actual practice question to really lock in this acceleration concept. A car accelerates from rest at a constant rate for 5 seconds. What is its acceleration if it reaches a final velocity of 15 meters per second? I'll give you a moment to think about it. Oh, and remember, that phrase, from rest, is a major clue. It literally means the starting speed was 0.
And the answer is 3 meters per second squared. Let's trace the math on that. We take our final speed of 15, subtract our starting speed of 0, which leaves us with 15. Then we divide that 15 by our time of 5 seconds. 15 divided by 5 equals exactly 3. You guys are going to do great on these equation questions.
Next up, Section 3, reading speed time graphs.
Okay, take a look at this specific speed time graph, tracking a car over a 10-second journey. Notice the overall shape it makes. We've got an upward slope at the beginning, a flat section straight across the top, and then a downward slope right at the end. The vertical axis is the speed, and the horizontal axis represents time.
So I want you to play detective for a second. Looking right at the middle of this speed time graph, what does that flat horizontal line actually represent? Like, what is happening to the car's movement during that specific middle section?
If you guessed constant speed, you hit the nail right on the head. On a speed time graph, a flat line means the speed is not changing. If you trace it over to the axis, you'll see the speed stays perfectly at 20 meters per second. This is a super common trick question, actually. A lot of students assume a flat line means the car stopped. But remember, the car didn't stop, it's just cruising along at a steady, constant speed.
All right, Section 4, all about waves. Let's do a rapid-fire review of the 3 main ways waves interact. First, reflection, which is all about bouncing, kind of like light bouncing off a mirror. Then there's refraction, which is bending. This happens because a wave actually changes speed when it enters a new medium, kind of like how a straw looks bent in a glass of water. And finally, diffraction, which is spreading, like a water wave spreading out after it passes through a really narrow gap. Just remember the keywords: bouncing, bending, and spreading.
Let's challenge you with a little wave math question straight from the exam bank. Wave A has a frequency of 10 Hz and a wavelength of 4 meters. Wave B has a higher frequency of 20 Hz, but a shorter wavelength of 2 meters. So, which one travels faster? Do you remember how to find wave speed?
Well, let's compare the two equations side by side to reveal the surprise here. To calculate wave speed, you just multiply frequency by wavelength. For wave A, 10 times 4 equals 40 meters per second. But for wave B, 20 times 2 also equals 40 meters per second. So as it turns out, both waves actually travel at the exact same speed. Pretty cool, right?
And finally, Section 5, Light and Sound Energy.
Now, let's explore a truly fascinating concept you absolutely need to know, the Doppler effect. This describes how sound changes when a source is moving towards you or moving away from you. Think of an ambulance siren passing by on the street. As it speeds towards you, the sound gets really high-pitched, but the second it drives away, the pitch drops noticeably.
So, as the sound source moves towards an observer, like the person standing on the right here, what exactly is happening to the frequency of that sound? Notice how those wave rings get all squished together in the front. What does that do to the pitch?
The answer is that the frequency gets higher. Because the object is moving forward, it's essentially chasing its own sound waves. This creates a much shorter arrival gap between each wave, and a squished wave means a higher frequency, which your ears end up hearing as a higher pitch.
And just like that, we've reached the end of our boot camp. You guys have mastered the momentum formulas, you've decoded some tricky graphs, and you totally understand wave concepts like the Doppler effect. Take a deep breath, trust your knowledge, and go get that top grade. But before we wrap up, I want you to remember something. These rules don't just exist on a piece of paper for a test, they literally govern how galaxies expand and how rockets reach space. So where else in the universe will you spot these forces in action today? Thank you so much for joining me in this explainer.